So today we're looking at the double angle identities, and just in the most general sense. This is on page 26 of your handout. In the most general sense, what are we doing today? We're applying the double angle identities to problems so that we can solve them. And here they are. This is the double angle identity for sine, and this is a very recognizable thing. In many ways, it's more recognizable than the sine squared plus cos squared. You're going to see 2 sine theta cos theta quite often. Cosine of 2 theta has a number of different variations to it, and I'm going to explain why that's the case in just a minute. It's very easy to confuse cosine of 2 theta. I'm using theta. I'll go to alpha if you like. Cosine of 2 alpha equals cos squared alpha minus sine squared alpha. Don't confuse that with sine squared plus cosine squared, because they are different things. Okay? And then we have these other two, and I'm going to talk about them in a second. And tangent, again, tangent is the weird one. And now that I see this and you see it, you're going to have to really make sure not to confuse this with the sum difference identities somehow, because they have some similarities. So those are the identities. Just take a minute and look at them on your formula sheet, make sure you know where they are. That pretty much concludes all of the formulas on the right-hand side of your formula sheet, which is all trigonometry. Let's take a look at this identity though. Cosine of 2 theta or 2 alpha is equal to cos squared of the angle minus sine squared of the angle. And you don't need to write this down, but I think it's useful for you to understand this. This is not a double angle identity on the right. It's the Pythagorean identity. But if I take a look at this double angle, and I can rearrange this. We've talked about this before. I can keep my eyes peeled for 1 minus cos squared or 1 minus sine squared. But if I take a look at the double angle identity for cosine, there's a sine squared in there. And sine squared is 1 minus cos squared. So I can replace the sine squared in the cosine double angle identity on the left with 1 minus cos squared. And if I do that, then I'm going to have cos squared minus negative cos squared, which is 2 cos squared, and then I will have that minus 1. And we have at least one example today where we make use of the fact that there's different identities for cosine of 2 alpha or 2 theta or whatever you want to talk about. And because we give you those 3 identities, you don't have to play all these manipulative games with the Pythagorean identity. Okay, and we'll get to that in a bit. On the other hand, if I take a look at the double angle identity for cosine, I notice that there is a cos squared in there. But cosine squared is equal to 1 minus sine squared. So I can replace that cos squared on the left with 1 minus sine squared. I don't need the brackets here, but I'll put them anyway. And then I have 1 minus sine squared, which is 1 minus 2 sine squared. So the bottom line is that's why we have this identity for cos of 2 alpha, this identity, and this identity. It's the only real identity we talk about in Math 30 that has a number of different choices. Okay. So let's take a look at some examples. Write each expression as a single trigonometric function and verify using your calculator. Well, example 1 is just really a warm-up type of thing. Since we know that 2 sine x cos x is equal to sine of 2x, and I don't need brackets around the 2x. Sometimes I will put them, sometimes I won't. That must mean that this is equal to sine of 2 times 15 degrees. So it's equal to sine of 30 degrees. Now you're asked to verify this. First of all, nobody should need their calculator to determine the value of sine of 30 degrees. It's a rational number of 1/2, right? You go to the unit circle, you look at 30 degrees, which is pi over 6. The y-coordinate is 1/2. But I want to point something out to you, and it's just a curiosity thing. It's not important. But I want to point out to you Well, first of all, let's confirm it. 2 sine 15 degrees, cosine 15 degrees. Make sure you're in degree mode. I am. You get 0.5. So we've checked that box. We've verified it. But the curious thing I want to point out to you is that sine of 15 is not a rational number. You cannot convert this to a fraction. It's an irrational number. And cosine of 15 degrees as well is an irrational number. So even though each of these little pieces is irrational, when you multiply them together, you get a rational number. Any questions with 1a? B, 1 minus 2 sine squared 20. You should recognize this. What you should recognize it as being is 1 minus 2 sine squared alpha. I'm switching from alpha to theta to beta to x. It doesn't really matter. And that's equal to cosine of 2 times alpha, which means this is equal to cosine of 40. And by the way, there's no degree symbol there, so even though if you left your calculator in degrees, you would still verify that they're equal, but we are asked to do it in radians. Sorry, I never finished that. When I try to convert that number from the previous question, cosine of 15 degrees, into a fraction, I can't. So put in my calculator in radians. What is cosine of 40 radians? It's that number. What is 1 minus 2 sine of 20 radians, quantity squared? Again, what I've just entered, my calculator is going to take sine of 20 radians and then square it and then multiply it by 2. And then take it away from 1, and you get the same number. Okay. I suppose we could, as an exercise, prove these identities to be true, but I don't want to. That didn't come out right. I don't think we need to. It isn't that I don't want to. It's not going to serve any real purpose. I mean, if you looked at this and you said, well, what is this thing equal to? I hope you would go towards your formula sheet and look for an identity that had that pattern to it. And the pattern is that this is tangent of 2 times that angle, which is tangent of pi over 6. And this is something that, again, you should be able to figure out what the tangent of pi over 6 is without a calculator. Pi over 6 is here. The x-coordinate is root 3 over 2, and the y-coordinate is 1/2. Tangent is y over x. Right? This is just a review here. You don't have to verify it this way. But this should be equal to, tangent of pi over 6 should be equal to 1/2 over root 3 over 2. And if I multiply the top and the bottom by 2, I get 1 over root 3. So this, without a calculator, we know that this should equal 1 over root 3. And if you were to multiply the top and bottom of this by the square root of 3, you would get 3 root 3 over 3 if you wanted it rationalized. Can you see that root 3 over 3? Barely. Let's just verify that by putting this into our calculator, which is a bit of a, that's not that big of a deal, but it's a little bit of work. Personally, what am I in? Radians, I would go 2 tan pi over 12. I guess I can use brackets for the bottom. Divided by brackets 1 minus tan of pi over 12, squaring the tan and closing the brackets on the entire bottom gives me this. And guess what? 1 divided by root 3 is equal to, it's equal to the same number. I should probably call this first example a warm-up, because that's all it is. It's getting you accustomed to seeing those patterns. Let's take a look at now a more involved question. An angle A is in quadrant 3, and tangent of A is equal to 5 over 14. Don't discount the importance of it being in quadrant 3. Sometimes you're told information that's, I don't know what the word is, erroneous. You don't need it. But sometimes you do need it. And because it's in quadrant 3, we should know that whatever we do, x and y will be negative. And I've put this box up here not because it would be given to you in the question, much like the last lesson. I'm putting it there to save us a bit of time. Okay? So you were asked to determine sine of 2a. Well, what's sine of 2a? It's 2 sine A cos A. But sine A is y over r, and cos A is x over r. And I've mentioned to you before, many times I'm sure, I like the idea in high school math of taking a problem that's a new problem and turning it into something you knew how to do before. And the simple fact of the matter is, if you know the tangent of an angle and the quadrant it's in, you ought to be able to find the sine of the angle and the cosine of the angle using the XYR thing, right? Tangent is y over x, which means that y must be negative 5 and x must be negative 14. Does that make sense? They're both negative because it's in quadrant 3. And that becomes a simple matter of finding r. It's the Pythagorean theorem. What do we have? Negative 14 squared plus negative 5 squared equals r squared. I believe r is root 221. Is that right? Okay. So we're just about done. The sine of angle A is negative 5 over root 221. The cosine of angle A is negative 14 over root 221. Multiply across the top, multiply across the bottom. If you can simplify, do so, and then you're done. What do we get across the top? Well, 2 times 5 is 10. 10 times 14 is 140. And negative times negative is positive. So I'm getting 140 over root 221 times root 221 is 221. I don't think there's any factors of 221 that are factors of 140. In fact, now that I think about it, I think 221 is probably a prime number. I don't think it's divisible by anything other than 1 in itself. Anyway, that's the answer. Any questions with 2a? Okay, so now what if I say to you, what is cosine of 2a? And I've given you this table here now, right? You've done the work, so there's no need to do it again. Cosine of 2a is cos squared of a minus sine squared of a. Don't really need the brackets there. So this is going to be, well, what is cosine of a? It's negative 14 over root 221. And we have to square that. Because cos squared means take the cosine, which is the negative 14 over root 221, and square it. Minus, we have to take the sine of a, which is negative 5 over root 221, and square it. I just maybe, I want to rewrite something or write something in addition to what I've written. I don't think everybody's going to need this, but this thing that I have here, that I'm highlighting, what it means, and I'm sure you know this, but maybe some of you might benefit from just seeing it. What it means is this. Right? That's what cosine squared of A minus sine squared of A means. It means take cosine of A and square it minus take sine of A and square it. So what do I get? I get 196 over 221 minus 25 over 221. I'm pretty sure that's fine. 196 minus 25 is 171. So it's 171 over 221. That's the cosine of the double angle. Oh, I wanted to do one other thing. This is not the only way to do the problem, because cosine of 2a is also equal to 1 minus 2 sine squared a. Isn't it? So we could have said 1 minus 2 times negative 5 over root 221 squared. When I square the sine, I get 25 over 221. So this becomes 1 minus 50 over 221. 2 times 25 is 50. 1 is 221 over 221. And when you put these together, in the numerator, you're going to have 221 minus 50, which, no surprise, gives you 171 over 221. And I won't go through, but you could do it with 2 cos squared theta minus 1, or 2 cos squared a minus 1. That would do the trick as well. And finally, in example 2, tangent of 2a is it 2 tan a on the top, 1 minus tan squared, 1 plus tan squared, minus. Okay. So this is equal to 2 tan a over 1 minus tan squared. One just final check. Anybody else agree with me on that? That is, okay. So tangent, we don't even need to do this table thing here because you were told tangent is 5/14. So any place you see a tan A, you can just put 5/14 in there. So 2 times 5/14 over 1 minus 5/14 squared. And every time I do an example like this, I go, oh man, sometimes it's okay to just use your calculator. You don't have to spend time crunching numbers. Well, I'll give you a minute to calculate what that is as a fraction in lowest terms. We all enter stuff differently in our calculator. I'm going to do it my own way. I get 140 over 171. So before we finish this lesson off with one final example, we're not getting really close to the end of the course, but you'll discover that as we get closer and closer to the end of the course, I tend to show you more and more methods to cheat on your calculator. Okay, you're writing a diploma exam, you see this, how can you get the right answer? Well, it's really not that difficult. I'm not going to write this down because, well, I guess I will write it down. See, what you could do is you could say, I know that they're asking me to use an identity because it's Math 30. But what I could do is find the reference angle by taking inverse tangent of 5/14. I would probably work in degrees would be my recommendation so you recognize what you're dealing with. So inverse tan of 5 over 14, that's a reference angle, that's not a rotation angle, right? That's not a rotation angle. You're told that it's in quadrant 3. I misspoke earlier about drawing something. I'm going to go back and talk about something in a bit. It's in quadrant 3, which means this reference angle plus 180 is the true rotation angle. That's A. I'm asked for the sine of 2A, so I'm going to double this and then take the sine. So simplify. You don't have many roads to walk down here or doors to open. Sine of 2 theta on the bottom is 2 sine theta cos theta. This is actually a simple question to simplify. In many ways, simplifying double angle expressions is easier than ones that we were doing before that involved the Pythagorean and the quotient and the reciprocal. Because you don't have very many options. Now, we do have options here. We have to subtract an equivalent expression for cos 2 theta. And maybe just lay your pencil down for a second. I hope you see that this is not a wise decision. Because if I expand this out, I will get 2 plus 2 cos squared theta on the top. And you may go, well, why is that not a wise decision? If I do that and I get 2 minus 2 cos squared theta over 2 sine theta cos theta, you can get there, but it's going to be more work. And I'm going to leave this up here and show you what you would do in a second. On the other hand, this is an even worse decision because now I'm muddying the waters with sines and cosines on the top that are difficult to deal with. You could still fight your way out of this. The smartest move is this. Because when you simplify that, you're just going to get 2 sine squared theta on the top. Right? I have 1 minus this 1 minus a negative 2 sine squared theta. Oh, that's perfect because 1 minus 1 is 0. We don't even need to worry about those numbers. And what I end up with is on the bottom 2 sine theta cos theta. So 1 minus 1 is nothing. So this is what you're writing down, right? I know I said lay your pencils down, but we're back to writing this down. I get on the top 2 sine squared theta over 2 sine theta cos theta, which is equal to sine theta over cos theta, which is tan theta. Just, just to make sure, you probably won't need to look at the bottom left of the screen this way, but this is the same as 2 sine theta over 2 sine theta cos theta. So we're dealing with factors that can be canceled. The 2's can be canceled. The sine thetas can be canceled. You're left with sine over cosine. Any questions with number 3? I did mention that if you chose this path here, that you can still get home with it. You can still solve this problem. you would factor a 2 out, because factoring is a strategy on that formula sheet, or that sheet I gave you. You can take a 2 out and be left with 1 minus cos squared theta. And you should recognize this as sine squared of theta from the Pythagorean identity. So it doesn't matter that there's one of the identities for cosine of 2 theta that gets us there quicker. The other ones will still get you there. So again, this is sine squared of theta, this whole thing. So you're left with the same thing, right? These are identical. And that's it. As I said, a fairly short lesson. Not nearly as many problems in this assignment as well, which means you should have some time, or you should dedicate some time to going back and continuing to work on those previous questions, because probably you didn't get them all done. I didn't expect you to get them all done. Okay. How many dollars was on that? Did you check yet? It was 15. Yeah, that's a pretty good deal. Yeah, no problem. Okay, and once again, there are some additional problems you can certainly practice. I'm going to just take my attendance, and then I will come around the room and help you out.